Okay, so last time we looked at the particle in the box. So let's call it a particle in a one-dimensional box. And so what was the potential of such a system? We drew that to be, so this is, if this is our x-axis. Essentially what happened is that the potential went to infinity in most places, except for a small region in the middle, right? Where the potential was 0. Oh, I'm having, good. So this was V of x, and this went up all the way to infinity, and this is plus L by 2, this is 0, this is minus L by 2. All right, and we said that we can have, say, 3 regions, region 1, and then this is region 2, this whole region, and then region 3. And what we started with the potential being a finite number, V0 was finite. And then we allowed V0 to go to infinity, right? And there we saw that in region 1, in the limit in which V0 goes to infinity, psi 1 in region 1 is 0. Similarly, psi 3 in region 3 is 0. So we have left is something in psi 2. Okay? And we found that, okay, we argued that, well, when the potential has an infinite or infinite, let's call it, it doesn't have to be only one, has infinite discontinuity, psi double prime of x also has infinite discontinuities, right? Because that's just the Schrodinger equation, right? The Schrodinger equation is second order in space. So, but when such things happen, psi prime, the first order, they can has finite discontinuity, okay? And that means that psi itself is continuous. So, we cannot have psi prime to be a continuous function, but we can have psi to be a continuous function. And what we said was that, okay, now in the region 2, we can write psi, which is psi 2, psi is 0th side. So in region 2, psi 2 is the only non-zero part. We called that A. Well, we call it A prime. Let's call it A tilde. Prime, because prime denotes derivative. So let's call it L tilde. E to the power I, kx plus B tilde e to the power minus kx. And this is something we know is the Schrodinger, is a solution to the Schrodinger equation. When the Schrodinger equation is given by, d squared psi divided by, well, d squared psi dx squared minus 2m by h squared e of psi equals to 0, right? Where E is a positive number. It is the energy. So this should be a plus sign here. Right? So, yeah. So here, K is defined to be a positive number, and that's defined to be a square root of 2me divided by h squared, or square root of 2me divided by h bar. Okay? So if I look at this equation, if I plug this guy into this equation, and well, basically what we don't have to, sorry, what I wanted to say is that this guy is the general solution to this equation for positive k, right? And the boundary condition at the boundaries between the three regions, like, there's this region, this boundary, and this boundary. If we match the boundary conditions, then we find two equations. From the left boundary, we get a tilde e to the power minus I k L by 2 plus b tilde e to the power I k L by 2 equals to 0. And similarly, a tilde from the right boundary, we get e to the power plus I k L by 2 plus b tilde e to the power minus I k L by 2 is equals to 0. Of course, this is we can express this as a matrix equation. If we do that, then we have a matrix of exponentials e to the power I k L by 2, e to the power I k L by 2, e to the power plus I k L by 2, and e to the power minus I k L by 2. This thing is acting on a tilde, b tilde, column matrix, and that must be equal to 0, 0. So this is a matrix equation. So this is m, and this is x is equals to 0. If x has a solution, that means that, m cannot be invertible, because if m is invertible, if the determinant of m is not 0, we can find an m inverse. If determinant of m is not 0, then m inverse exists, right? If m inverse exists, then this equation tells us that x must be 0. So that means that there is no solution. So we must assume that, we assume that determinant of m is 0. So if I calculate the determinant of this matrix, what do I get? I get a condition, and I get the condition. So what is that? If I look at the determinant, so we are going to have this multiplying this minus this multiplying this, right? So this is just very easy to calculate. The first, we get e to the power minus I k L minus e to the plus I k L, but this you realize is twice I, the sine function. So we write this as sine KL is equals to 0, and the solution to this is KL is n of pi, and n can be integer at this point, right? So we're actually not going to, we are going to come back to this equation. This is not the, we are going to see that we are not going to get a solution to the energy condition for all values of n, for all integer values of n.